Okay, so today, like I said, we are going to talk a little bit about basic electronics. I know I probably, in the future, when I teach this class, I will do this week instead of going back to it now. A little out of order, sorry, my bad. First time this class has been taught, so bear with me a little bit on that. The test is going to open on Wednesday. It is going to be open until Saturday. Please be aware that it's not open for a week like most things because it's a test, unlimited the days that you have to look it up. For some reason you don't get it taken between Wednesday and Saturday, you better let me know in advance why you're not taking it, and you better have a good reason. No makeup work, remember? All right. So, also remember, we will not be having class Wednesday because I have to go to the majors fair. So if any of you are interested in finding out more about majors on campus, or if you haven't, firmly fixed yourself in computing or computer science, there's going to be a majors fair in the University Rec Center over here. From, I want to say it goes from 11:30 to 2, something like that. I just know that it goes through our class, so I will still be over there handing out information because we got to recruit more people into computer science and computing and math.
And text doesn't sort itself.
Yeah.
Yeah.
Yeah, it will one day, maybe. So I want to start off with some basic definitions and talk about some basic information. So voltage is important. We do there's a lot of things, like you have a 5V port, you have a 9V battery. Well, the V is voltage. That's how it has a very formal definition, which you can see up here. It's the electric potential difference between 2 points. It's the force that pushes electric current through a circuit, measured in volts. It's how strong it is. How much power, how much electricity is going through that line at that time. So your battery is a 9-volt battery. The Arduino usually needs things to be more like 5 volts. It has a 5-volt input. And then we have resistors and capacitors that will impede or increase that voltage based on what we need it to do. But voltage is very important because some of the components that you have in this kit have a limited voltage they can take. And if you overdo it, you will burn them out. Hence the smoking smell and the electrical burning smell we have had in class. And I have one student who reported that their Arduino board actually smoked. I think that was a manufacturing error, but not positive. So voltages are important. Making sure that you don't plug in too much voltage is an important thing. So it's probably not a good idea to have your Arduino board plugged into your computer at the same time you have it plugged into the battery. I hope that they have built something into the board that doesn't allow both to go through, but that's a hope because I don't know exactly who built this board and how all of the circuitry is done. So the potential refers to the possibility of doing work. A lot of electronic stuff is based on how much work, horsepower, how much you're going to accomplish with it. We're not going to get into the math of it because that's physics and electronics and engineering. And if you want to know more, please look it up. So 1 volt is a measure of the amount of work required to move 1 C of charge. What's a C? I don't remember right off the top of my head. But it's going to move stuff through, we're not gonna do the math.
Yeah.
I'm not gonna give you the formulas might pop up here in a minute for Ohm's law and stuff like that, but we're basic knowledge here, no math, no mathing in here today. Or current is the flow of the electric charge. It's measured in amps or amperes. It represents how much charge is flowing in the circuit over time. Yeah,
So earlier on the volt slide, you denoted like the electrical difference between 2 points. So what exactly could that be physically? Just one side having more electrons than another side?
well, electricity is constantly moving.
Okay, yes.
So if it's not getting through whatever conduit it's using,
It's not plugged.
then the difference is stark, because you could have 0 at one point and 9 volts at the other because it didn't transfer.
Mhm.
So you see what I'm saying? There's always a difference in places because you lose a certain amount of power over distance too. And what we're doing here, you're losing is negligible because we're using 4-inch wires, you know. But over very long periods or very long spans, you could lose voltage.
Okay, fair enough.
I'm gonna be honest with you, you guys are always, you know, we have surge protectors on our computers and power strips and stuff. Surges are bad, absolutely, but a brownout is almost worse.
Brownout, you mean blackout?
No, brownout. A brownout is when the current drops or the voltage drops but doesn't completely go away, so it's underpowering things. And a lot of times with computers, that is actually worse than a surge because we have so many surge protectors built in to shut things down. But we don't necessarily have a way to go, oh, I'm getting some electricity, but I'm not getting enough. Back in the dark ages of my career, when I was actually installing Cisco switches and routers, the brownouts were actually worse than the surges for our switches and would burn them out faster because they were trying to do too much with too little voltage.
So do you,
So that's why we have battery backups now on computers, because the battery backup gives a consistent amount of electricity going through.
yeah,
So
it provides a consistent current?
yeah, it does a lot of things. We're not gonna get into the how all that works, but current, like I said, is the flow, right? You have to get the electrons from one place to the other. The charged electrons cause the electricity.
Hopefully, the current is less.
Current works better and flows better on things that are highly conductive.
Yep.
That's why most of our stuff is done with copper wiring, because copper wiring is highly conductive. It's a great conductor. You have very little loss over the flow. Water is a good conductor, which is why they tell you not to be taking a shower during an electrical storm, because it will flow through the water, not the pipe, to you. Yes.
Isn't water actually a poor conductor of electricity, but it's the minerals dissolved within the water itself?
Not getting into the details of that.
Okay.
Water conducts electricity. That's all we need to know here. You can go take chemistry or biology or whatever it is and learn all that. For our purposes, water conducts. It's not a great conductor, but it is a conductor.
Yeah.
It also will short out your board because when you spill water on your board, you now have connected a whole bunch of things together.
Which don't.
Just don't turn it on, dry.
Yeah, definitely want to turn it on dry. I'm going to tell you though, I want a funny story about a phone that should never work again. I somehow forgot that my phone was in. This is really sad.
The washing machine? Yeah.
So I put my phone inside of, we had just dug up a big trench and I had a bunch of muddy clothes and tennis shoes and stuff that needed to be washed. And I slipped, my hands were full, so I slid my phone into the inside of my tennis shoe and then forgot. And then I threw all the tennis shoes into the washing machine. Not only did I wash this phone completely through the entire cycle, it was still on when I opened the washing machine. And I cracked the knot out of the string. The
Why?
tennis shoe messed up my string. But it still works. It took me 3 days to dry the water out of the phone lenses, the camera lenses. But after that, it was fun. So, more to that story is don't wash your phone. But if you do, immediately turn it off where the electronics are not still running. And price works. Takes a while, but it works. All right, so do we understand what current is? It's how the electrons are flowing. It's the direction. It's the path. It's moving from one point to the other.
Like flowing water that you don't want on any of this.
Yes, sort of. Amperes, we're not going to deal with as much in here. There are some things that will tell you how many milliamps or amps something is providing. It's kind of the intensity. We're not doing the math. You can, the formulas up here, but we're not actually going to measure any of this. Just be aware when you're doing and building these kits that if it says you use a resistor, that you pick the right ones and that you make sure that you're not over voltaging or under voltaging any of the parts. Electricity only works if you have a closed circuit. The power for the light bulb doesn't come on if the circuit's not closed. Your light switches actually open and close the circuit. When you turn the light switch off, you have broken the circuit. So now electricity is not getting to the light. Something's blocking. Yes.
Just to make sure my memory isn't extremely short, doesn't a button also work by simply pressing cover plate down?
Yes. Buttons are the similar. They're turning the current on and off. They're making a connection. When the button's pushed down, generally means that the connection's going through because it connects the circuit all the way. When you let it up, you broke it.
Intentionally.
Intentionally, yes. So an open circuit is going to have something, a resistor, a switch, something that breaks the flow, and then you can turn it on and off as you need, depending on that. You don't have to have a question for every slide.
Those two both.
All right, so the direction of flow is important. That's why we have polarities on those LEDs. The direction of flow can kill some of your components or keep them from properly engaging. Yes, sir.
I mean, by definition, being a diode, it only allows flow in one
We'll
direction.
get to diode in a minute. I have a slide on diode. All right, so we're going, you have to be aware of this. You have to be aware of polarity. You have to be aware of directional flow. Conventional currents go from the positive side of the battery through the load and the resistance or whatever you're powering back to the negative side of the battery. That's the reason grounding and positive and negative are important. You have to have a place for the electricity to flow to. So a battery is a direct current. Our electrical lines that run houses and stuff are what we call alternating current. So direct current has one flow direction. Alternating current can change and does change. What we have in the wires and stuff, our alternating current will go in one direction and then at some point change and go back the other direction. It's important, but in our case, as long as you wired everything correctly, It should not be necessarily a determining factor because our board takes direct and alternating current. It's an electrical addition. Right? And some of you are going to say, that's not exactly right. And it may not be 100% the most detailed description I've given you on these things, but I'm not teaching an electronics course. I'm teaching the basics where you don't burn up the physical devices in our hands. Is there a lot more details to this? Absolutely. And if you're interested, I highly recommend a physics course. I enjoyed physics when I took it, except for math. I did not like that. Way too much math there. Resistance. That's what we need to start learning about because we want to use our resistors accordingly and correctly. It's the opposition to the flow. It slows it down. It's a roadblock. It throttles it back. Take a turn, but it causes it not to be wide open flowing through there. If you have too much flow going through wires, you can make them hot. You can create a fire. That's the reason modern electrical cables are all insulated because they want to keep. You don't want to have fire. You don't want to have cross circuits. You don't want to short things out. Really old electrical wiring actually had cloth coverings, which is not great. But at the time, we didn't have all these modern plastics stuff that they do now. My parents' 1930-ish, 40-ish home was originally built way back when they had what they call knob and tube wiring. And we ripped out part of my parents' house thinking that it had a electrical update at some point, and it had not. It still had the black non-grounded electrical wiring and some of the core components of their house. How that house did not burn down, I have no idea because it literally looked like they had taken all these cables and just knotted them together in some places. It was bad. So be aware, old electrical probably needs to be replaced. If you're buying a historic home, have the electrical check. Yes.
I was just wondering on the section about them using cloth around wires, how old are these wires? Because synthetic rubber was made around 1909.
Yes, but it wasn't really massively produced back
Fair enough.
then. It actually came from rubber trees and.
Yeah, before that.
Yeah.
I was speaking of synthetic.
So I want to say their house was built in the 1930s and 1940s, but I don't know for sure.
Mhm.
All right, insulators are the key in this. They have a lot of resistance. Why you will see electrical wires with insulators around them to keep it in the wire.
Yep.
You'll also see people that are working on high voltage and other even low voltage wires, but mostly high voltage wires will wear clothing that is considered insulators, natural fabrics, rubber soled shoes, anything to keep them from creating a closed circuit with their body and the electrical wire. Because your body is conductive. It's not the best conductor in the world, but it is absolutely conductive. So resistors, we've already talked a little bit about them. If you read and watched the videos, they talk about them. Resistors are a good way to control voltage and current because you can artificially or physically change how much resistance they are based on which resistor you pick. It impedes the flow. It keeps everything constant and consistent. The resistors, and we talked about this a little bit, I know earlier in here, that the color bands tell you a lot about the resistor and what its measurement is or its rating is. So the number goes with the first band is the first number, the second band is the second number, the third band is the number of zeros or the multiplier for that. So they're condensing the number down. Fourth is tolerance. So each band means something. Each color means something. So your kit actually came with a little card that has the color codes on it. I don't know if you paid attention to it or not, or if you just picked the one that had the right label on the packing material for what it needed. But it does have a color code on it. So if you, for some reason, had them all loose and you needed to know which resistor it was, you could look up the color code and the band strips and figure out which one it's for. Right? Am I going to ask you to memorize this? Absolutely not. That's why you have it on a card. That's why you have the internet. This is something that is just easily accessible data that you can look up, and I see no reason to ask you to memorize this. I don't even think you necessarily have to memorize what all of the bands, what order the bands are in. Because again, you can go look it up and know that the first one is the first number, the second was the second number, third was the multiplier. You can go look that up. I'll be honest with you, I didn't know that. Not instinctually, I have to go look it up because I learned it, and then I'm like, oh, I'm gonna use that for a decade, and then I forget it, and then I come back to it. And I look it up when I need to know it again. Units are absolutely important. I don't know if you guys understand some of the units that we even talk about in some of your other computing classes, like we talk about nanoseconds and kilobytes and gigabytes and terabytes and stuff. I don't understand if you guys have a concept of what that is. So in electricity, it goes down more than up. So it's talking about tiny, tiny little pieces. So we're talking about nanoseconds. A nano is 1 trillionth of a second. So computers do so many processes per nanosecond. That's the reason it looks like a computer is doing multiple things at the same time, when actually most computers can only do one task per core. So they're a multi-core computer, it's doing more things. But to us, because it's such a small fraction of time, it looks seamless. So just be aware of these. Kilo means it's 1,000. In computers, it's 1,024 because we do it in bits and bytes. But in electricity, it's 1,000. Right? So kilogram and milligrams and stuff like that. So this is close to the same as data, but it's slightly off because of the 8-bit. This would be more in line with what you learn in elementary school when they're trying to teach you the difference between standard measurements and the metric system. Right? We all maybe sit through that. Because we're one of the few countries in the world that still uses the standard system or empirical system instead of metric system. I kind of get the metric system. Okay, it's that Fahrenheit versus Celsius thing that always kills me. I never can convert that right. All right, so Ohm's law, I want you to be aware of it, but we're not actually going to probably ever calculate it ourselves. So Ohm's law is the amount of current in a circuit that is dependent on its resistance and the applied voltage. So you take the voltage divided by the resistance, and you get that is Ohm's law out of it. So you know what the impedance and what the actual flow is. Does that make sense? The general level. Feel like I've lost the background. You're all like zoomed out on me. You're all good. Okay, second. I know I'm boring. Boring stuff. Power is measured in watts. So kilowatts, megawatts, whatever watts. You have a 60-watt bulb in your light fixture at home. That's how much power is being produced in that bulb. Or that bulb, how much power that bulb has the potential for. Because you can put higher wattage bulbs into sockets that they're not really designed for. I'm going to burn the bulb out quicker that way. I know, like in my house, I have a bunch of ceiling fans, and most of them are rated for 60-watt bulbs. This kind of flew out the window though once we came up with LED light bulbs, because they run at a much lower wattage. They produce a lot more looms, which is the measure of how much light they're putting out. So you get more light for less electricity, which is good for your power bill. Volts times amps gives you the powers in watts. How much voltage you have versus how much amperage you have gives you watts. Again, not going to do any of this math because it's not physics. This is physical computing. So this is the big thing. We have capacitors. They're in your kit. If you're looking at a printed circuit board, they'll often look like the round barrel-shaped ones. You will have some of the others too, but for the most part, if you look at the inside of your computer, which I'm hoping to have the very least video and slides of on Monday, hopefully here in class we'll have a real computer to take apart, even if I have to bring one from home. But the capacitors are built onto, some of them are built onto your motherboard, some of them built onto your sound cards, your video cards, anything that has to have extra or different power needs. They're measured and they have a measure of their own. I'm not even gonna try to pronounce these things. Some are polarized, some are not. So sometimes you have to have the positive and the negative correct. This depends on how it was designed and who made it. I will tell you that they store electrical energy. That means that even if your computer or other electronic device is not plugged in, there still could be some amount of electricity still stored in that capacitor. And it could be stored in that capacitor days, months, years even in some cases after being unplugged. Now, this is not as big a deal to you guys at this point, but back in the day when we had the CRT monitors, the big heavy monitors, you might remember them from your childhood. They actually would have some capacitors in them that would hold charges for very long periods of time, even after being unplugged. And it was enough that it could do you some physical harm. Maybe you have like a heart condition or something, it could even potentially kill you if you didn't discharge the electricity in the correct way. So don't play with old TVs and old monitors. It's a very slim possibility this will ever happen. But just be aware you can get shocked.
Mhm.
These little capacitors usually aren't storing enough to do much damage, but you might get a jolt out of them. You know, yes, sir.
What's the difference between a capacitor and a battery?
Capacitors are hardwired in. Batteries are portable and sometimes rechargeable. Capacitors also don't initially come with a charge. They can store a charge while in use and if they're hooked up. But if you want a real detailed definition of the difference, Google is your friend. And also, in my experience, most capacitors store very small amounts. And it's usually temporary. Very, very rarely a capacitor is really holding months, days, and years worth of electricity. Polarity the capacitors that have polarity need the shorter terminal always goes to the negative side, the longer terminal positive, just like your LEDs, right? Just be aware of that. A diode. Now, I don't know if we've talked about diodes. I'm pretty sure we haven't. But they're a one-way gate or valve for electricity. They only let it flow in one direction. See, we talked about alternating current. Diode would not allow it to come back. It ideally has zero resistance because we just want it to flow. We don't want it to stop it from flowing in the direction it's supposed to be. Only stops it in the direction it's coming back from. So it has zero resistance in the flow direction and should have the most resistance, or they say infinite resistance, in the other direction. So it should 100% block it from going the wrong direction. The world is not perfect. You can burn out diodes, you can mess them up. Things can be broken. Diodes though will protect. So say like with solar panels, if you have an abundance of electricity, you can sell it back to your electric company, right? So that means that the current can flow back the other direction. However, there are times where you don't want this to happen. Like if you're hooking a generator up to power source, you don't want the flow to go backwards because then you're going to mess up your generator. So that's where a diode or a switch for that would come in handy to keep the flow from going in both directions. But in the case of where you want to sell your extra electricity back to your power company, then you want it to flow both directions. Now, when your power goes out and you're living off your solar, you also want to be able to turn that switch off because you don't want to give the power company the electricity that you need in your house. Ask me how I know these things because my husband wants to put solar panels on my roof. Which is a lovely idea, except that we live in a very wooded area and all of our houses in shade most of the time. So I don't think he's going to get what he wants out of it. But it is what it is. So we use diodes for circuit protection. We keep the polarity. We always want to be very careful with polarity because if you don't have the polarity right, you're going to fry something eventually. If you don't do it on the initial connection, you're going to do it very quickly. How many of y'all put the LED on the 9-volt battery when we went to
The garage.
the garage backwards and immediately burned it? Right? Some of y'all saw that happen, right? It just flashed really quick because it was dead that quickly. Yeah. So it could be that quick or it could be a slow thing.
Mhm.
So we know what an LED is. Put it in here just where we have it all in condensed place, but we all done LEDs. Remember, positive is the longer leg, negative is the shorter leg. If you ever forget, most of them have a flat side, which indicates the negative, or sometimes people have trimmed up the wires and you can't tell which one's longer and shorter, or you bent the snot out of them and So just be aware. We all know what our potentiometer or variable resistor, which is easier for me to say and a lot easier to spell to me than potentiometer. But you turn the knob and it increases or decreases the resistance based on which direction you're turning it. So volume switches basically are potentiometers. We used it on our light, follow the line module to increase the sensitivity and decrease the sensitivity. Things like that. Back in the dark ages when everything was knobs that basically were digiometers. Y'all are not old enough if you remember having knobs on television to change channels and stuff either. So.
Oh, that part, the tennis.
No. The actual changing of channels. There's a reason that old folks say, I need to turn the channel or I need to turn the channel because I was a kid, it had a knob and you put it on 2, 5, 11 or whatever channel you were going to. Also the remote control was me. Hey, go change that. Y'all just don't know how easy you have it. Transistors. You've used them, but you don't know you've used them because the board has transistors built into them. Your computer motherboard is just a whole bunch of transistors in a lot of places. As a semiconductor device, it amplifies and switches electronic signals. Originally, computers were a whole bunch of transistors. They were either on or off. They switched things back and forth. They did calculations based on those.
Mhm.
Now they're so small. So we did a little bit of this with some of the car parts that had the three prongs on them. So the 3 prongs, power in, power out, and some sort of control. So voltage or current is applied to one pair of the transistor terminals, so positive, negative. It has a semiconductor inside, does stuff. The base pin, I don't want to get in a lot of the physics. Just let's agree that it works. Are we okay with that?
Occasionally or something involving experiment.
Let's just agree that it works. It's on or off, it makes decisions, it switches back and forth between states. If you go take an engineering course, or you decide you want to be a computer engineer, you want to build hardware, you're gonna have to get a different degree. That will go into more detail about this one. I have a son that's doing this. He's in physics right now, freshman year of college, taking physics because he needs that for his engineering. And he's taking multiple electronics courses coming. I'll make him come and teach this class when he gets through the electronics courses. Or at least this lecture of this class. Because I enjoy doing that to him. So this is actually, this picture shows the integrated circuit. Your board, the actual brains of your Arduino is that long microchip that's attached. It should be removable, but I don't know for certain that yours hasn't been soldered in. So please don't go and try to pry it out, but generally speaking, they are removable and they plug into the printed circuit boards. But they're interchangeable. Your computer has a processor in it. Processor is removable from the circuit board or the printed one of the boards because you can change them out. A lot of people don't nowadays. Most people don't know how to work on their computer and the different components inside of it, which is a shame. But they have started building computers, especially in the last decade, to be disposable. They don't intend for you to fix them. It's more cost effective or not so outlandishly cost ineffective to just replace the whole computer as it is to replace certain components. If your motherboard or processor goes bad in your computer, then we're going to spend almost as much as a new computer just to fix those two parts. So most people just replace. If your CD-ROM dies, you can swap that out fairly inexpensively. If you need a new hard drive, you can add that fairly inexpensively. But a lot of people don't know that and don't want to know that. My husband is currently fixing an Alienware computer in our house because the solid state drive went out on it. All the rest of it's working, but the solid state drive is not booting. So he ordered another solid state drive to put in it, where we can see what else is going on. Now, if the motherboard is fried, which we won't know until we get the new piece in, then the computer's a total loss. But he can still use that solid state drive he just ordered in one of our other computers. But make my son very happy that his computer didn't work in his room anymore. See? Question.
Does micro in the context of microchip just mean very small, or
Yes.
is it specifically the, okay, it's not referring to the unit micro?
It might be, but in this day and age, it's mostly, it might have started out that way, but now it's very small. It's tiny. There are potentially, depending on what kind of processor you have, millions of circuits.
I am terrified of the prospect of a 1 million times size chip.
We've about reached the point where chips can't get much smaller.
Yeah.
We've reached a point where
Yeah, but
the heat produced and the size as kind of, it took them a lot longer than they originally thought, but I think we finally reached that point. So we're going to start learning some new technologies to get much smaller.
yeah.
That's why they're working on nanotechnology and stuff like that. We're making it that much smaller.
We're not talking about that right now.
Yep. Different class. So this is a printed circuit board. So all of the components that we've been using communicate with each other through a printed circuit board. The green portion of your R3 board is a printed circuit board. Those are electrical, all the silver you see on it are electrical wiring connecting things together. All the solder points, the little silver bumps that are sticking up, potentially are shorting points for your board. If you connect two of them together incorrectly, or if you set them down on a metal conductive surface, you could short your whole board out if it's plugged in at the time. If the power's not running through it, not a problem because there's nothing short. This is why I would say that you should always unplug the power source from your Arduino board while you're recabling and rewiring. Because it's really easy to touch two of those wires together or to accidentally put it in the wrong slot. Those pins are incredibly close together. And if you're like me and have vision problems, incredibly hard to read the labels on some of them. So always make sure your wiring is correct before you start applying power. So they're printed and they're kind of, and they're labeled and everything on the front of the board. Resistor number, resistance, value type, clarity, etc. is sometimes included here. So solder both sides, there's directions here, there's pin numbers here, there's voltages. So there's the different labels mean different things. So they'll have codes on them and they'll come with documentation to tell you what the codes mean. These are talking about resistance. This is a 100K resistor. This is a 47K resistor. But it's all printed into the board instead of being individual pieces. The holes go all the way through the board from one side to the other. Where you put soldering points through them or screw them down to mount them to a case if there's nothing in them. The back of the board doesn't have labels and stuff on it, but it does often have those bumps that I'm talking about. These are the solder points. They're not as smooth on the back. So I actually have seen some pretty silly things happen when I was teaching high school. High school students are not known to make good choices. We were taking a computer apart, talking about the different internal pieces. And one of my students thought it was a really good idea while the motherboard was laying on the metal cover to the case to plug power supply in. It not only shorted out the entire motherboard, it actually shot sparks out across the metal board directly at me, which almost got expelled. But likely for him, his parents are somewhat important. But don't plug in things. Don't add power to a circuit board if it is touching a conductive surface. If you do open your computer, and if I do get to bring one in, I will show you that most cases have risers for the screws to go into that keeps the board elevated off of the rest of the case. And that is very important. That's why you have to match the motherboard to the case format where they don't accidentally have any contact points. And that is the gist of what I wanted to talk about today. This will not be on this week's exam.
What we just talked
What we just talked about is not on Wednesday's exam because I wanted to give you time for it to digest. Now, the different parts are because we've used them, but I mean, the extra added info here probably is not going to show up. I don't think we really covered anything that hadn't already been covered in the labs, but that's where we're at right now.